Hi, welcome to today's lessons. Today we're going to go over lessons 8.5 and 8.6. So you're going to learn a couple new terms and review some stuff but put definitions to them, such as trapezoids and kites, and then we're going to go over all the different special quadrilaterals that we have learned in Chapter 8. So let's go on to the next slide. The first thing that we're going to do is define what a trapezoid is. So by definition, a trapezoid is a quadrilateral with exactly one pair of parallel sides. These parallel sides are called bases. So let's take a look at our quadrilateral or our trapezoid that we've got here. So we've got trapezoid ABCD. We have exactly one pair of parallel sides. So this side right here and this side. So side AB and side CD are parallel to each other. These sides are called your bases. So side AB is a base, and side CD is also a base. And excuse my handwriting, I'm still learning how to walk or how to write with this new technology. Okay, so next if we move on to the next part of our definition, we have the non-parallel sides are called legs. So that means side AD would be considered to be a leg, and side BC is a leg. And then lastly, a trapezoid has exactly two pairs of base angles. So what we mean by this are the angles that are on the base. So angle D and angle C, those are base angles, and they're not necessarily congruent to each other. So that's why I marked it with one line here and two lines over here to show that they're not necessarily congruent to each other. That's one pair of our base angles. The second pair would be angle A. So we'll go ahead and mark that different as well. And angle B. So those are our base angles. Okay, so now that you have the basic terminology down for a trapezoid, let's go into a couple of specific examples. So now we're going to learn about an isosceles trapezoid. So an isosceles trapezoid is unique in that the legs of the trapezoid are congruent. So by definition, an isosceles trapezoid is a trapezoid, but the legs are congruent. So in this case, AD would be congruent to BC. And we're going to go on to the next slide and learn a couple of new theorems that pertain specifically to isosceles trapezoid. Okay, so let's go on to the next slide. Our first theorem is theorem 8.14, and this says that if a trapezoid is isosceles, then each pair of base angles is congruent. So remember, we already have an isosceles trapezoid, so that means that we know its legs are congruent. So again, remember the legs are the non-parallel sides. So we know that the legs are congruent. But what theorem 8.14 says is that each pair of the base angles are also congruent. So now we know that angles D and angle C are congruent to each other, and angle A and angle B are congruent to each other. So that's what theorem 8.14 says. Okay, so now we're going to move on to theorem 8.15, which is the converse of theorem 8.14. And theorem 8.15 states that if a trapezoid has a pair of congruent base angles, then it is an isosceles trapezoid. So what this is saying is that we just have to know it has one pair of congruent base angles. So for example, if we knew that angle D and angle C are congruent to each other, then we know that it is an isosceles trapezoid. So unlike theorem 14, which says each pair of base angles is congruent, the converse is that we only have to have one pair of congruent base angles to know that that's a trapezoid. And finally, the last theorem, 8.16, says that a trapezoid is isosceles if and only if its diagonals are congruent. So that means, if we take a look at our trapezoid again, so if these diagonals, so if AC is congruent to BD, then we have an isosceles triangle. So we know that AC is congruent to BD, or the length of AC equals BD, then we have an isosceles trapezoid. Okay, so now we're going to move on to another theorem. We have more theorems and definitions. Now we're going to go back to our triangle days where we had the mid-segment theorem for triangles. Well, we also have one for trapezoids. That's theorem 817. This theorem says that the mid-segment of a trapezoid is parallel to each base and its length is 1/2 the sum of the bases. So let's take mid-segment MN. So you can see it just popped up on our trapezoid there. MN equals 1/2 of AB plus CD. And according to the theorem, MN is parallel to AB and MN is parallel to CD. So let's take an example here. Let's say we are given the information that AB has a length of 8. And let's say CD has a length of 10. From our theorem, we have our equation right here. We know that MN equals 1/2 the length of AB plus CD, so we can figure out its length. So MN equals 1/2 of AB, which is 8, plus CD, which is 10. So that means that we have 1/2 of 18. So MN has a length of 9 units. So that's how you can put this theorem into practice with actual examples. Okay, now we're going to learn a new definition, and that's about kites. So the figure that we have to our right, our quadrilateral ABCD, is a kite. And by definition, a kite is a quadrilateral that has 2 pairs of consecutive congruent sides, but opposite sides are not congruent. All right, so let's go into that a little bit more. So it has 2 pairs of consecutive. So remember, consecutive means that they have to be next to each other. So this means, by looking at it, AB would be congruent to BC. And 2 pairs means that we have 2 pairs of them. So that means CD is congruent to AD. BC would never be congruent to AD. Those would be opposite sides here because they don't touch. And AB would never be congruent to CD. Again, those are opposite sides. So by definition, a kite has 2 pairs of consecutive congruent sides. So that means that they're going to share a vertex in common for them to be consecutive. So side length AB and BC has vertex B in common, and side AD and DC has vertex D in common. So now, of course, we're going to have some theorems. So theorem 818 says, if a quadrilateral is a kite, then its diagonals are perpendicular. Okay, so let's draw these diagonals. So we have a diagonal that can connect vertex B with vertex D, and we have another diagonal that can connect vertex A with vertex C. And what this theorem says is that their intersection forms a right angle. These are perpendicular to each other. Okay, last theorem. If a quadrilateral is a kite, then exactly 1 pair of opposite angles are congruent. So I'm going to go ahead and clear the information that we have on here and identify which angles are congruent. So if a quadrilateral is a kite, so remember it has to be a kite, meaning that it has consecutive sides that are congruent. So let's mark those again. Then it has exactly 1 pair of opposite angles are congruent. So those are going to be the pair that connects the shorter side with the longer side. So angle A and angle C will always be congruent if this is a kite. And that's what theorem 819 states. Okay, now we're going to move on to a couple of examples. So we need to find the measures of the remaining angles given this trapezoid. We know it's a trapezoid because we have 1 pair of parallel lines. And remember, by definition, that means if we have 1 pair of parallel lines, we have a trapezoid. We also know it's an isosceles trapezoid because we see that the sides, the legs, are marked as congruent. So going back a couple of lessons, we know that a quadrilateral, the interior sum angles of a quadrilateral is 360 degrees. And since this is an isosceles trapezoid, we know that angle B is going to equal 50 degrees because our base angles have to be congruent. So angle B also equals 50 degrees. So now we just need to find the angle D and angle C. And again, these will also be congruent angles by definition of an isosceles triangle. So we have 360 degrees equals 50 plus 50 plus angle D plus angle C. However, we know that these two angles are congruent to each other. So now if we simplify this, we get 360 equals 100 plus 2 of angle D. All right, let's solve algebraically and subtract 100 from both sides. So now we know that 260 degrees equals 2 times the measure of angle D. And if we divide both sides by 2, we can see that the measure of angle D equals 130 degrees. Oops, sorry, I didn't put D there. It should be a D right there. That's also the measure of angle C, because they're congruent. So we know that the measure of angle D is 130 degrees, and the measure of angle C is also 130 degrees. So we've done it. We've solved everything that we needed to. Let's move on to the final slide. So on this slide, we've got a question, and we want to find out what type of quadrilateral has at least one pair of opposite angles congruent. So below, you'll see all of the different kinds of quadrilaterals that we've learned in Chapter 8. We've got a parallelogram. So here's our parallelogram. We've got a square, a rectangle, a rhombus, trapezoid, and a kite. So we've got to figure out what type of quadrilateral has at least one pair of opposite angles congruent. So by definition, or by our theorem that we have for a parallelogram, we know that opposite angles of any parallelogram are going to be congruent to each other. So for a parallelogram, we know that we have two pairs, which definitely fits because our question's asking for just at least one pair. So all 4 of these quadrilaterals fit that question. They answer that question because remember, square, rectangle, and rhombus, they're just special types of parallelograms. So all 4 of these quadrilaterals have at least one pair of opposite angles congruent. So now let's move on to a trapezoid. So remember, for a trapezoid, opposite angles are not going to be congruent. Base angles could possibly be congruent if it's an isosceles trapezoid, but opposite angles will not be congruent. So trapezoid does not fit this definition. And kite, we have a theorem that says that the opposite angles, or exactly one pair of opposite angles of a kite, will be congruent. So a kite works as well. Okay, so that is it for today. Thanks so much, and see you guys in class. Take care. Bye-bye.